hope, what are some of the big kind of unsolved mysteries that you're looking for in your research into supernovae? What would you like to know?
Ooh, how long do we have?
About 3 minutes.
One of the biggest questions is we use these specific type, these thermonuclear events. So these are the giant white dwarfs that explode. And we don't understand exactly how they blow up. And, the way we use supernova is if you know how bright something is and how bright it should be, you can calculate the difference in brightness and get a distance. But if you don't know how bright, if you know how bright the bulb is, it works. But if you don't really know what kind of bulb you have, then your measurements are a little bit off. And these are one of the biggest things that we're trying to address, and how to use that bulb better. And we need to find these things earlier and quicker so we can get as much data as possible. And that's where, the people are literally helping us. We would have to spend hours, each person on the team, every day doing our science, all the processing, analysis, database stuff, in addition to finding them. So by allowing these people to help us find them, a key part of this, we can be more efficient and quicker and start to answer these questions.
I mean, I think, if I understand, the type 1a supernovae, those are the ones that are this material accreting onto this white dwarf, and then the white dwarf explodes, and that gives you that standard candle to be able to know how far away those things were. But, I mean, is there a way potentially to use other kinds of supernovae as standard candles as well, if you learn more about them and what you sort of see in the detonation?
So people have tried. There is a huge effort to do that. But the advantages of type 1a is that they're easy to standardize. And the other ones, you need a lot of parameters, and there is a lot of uncertainty there. But also type 1a's are very bright. So if you compare it to like a type 2 supernova, we can see them, like type 1a are much brighter, so we can see them further away. And that's a huge advantage, because we couldn't probe the acceleration of the expansion of the universe with a supernova that were only close by. We need to go very far away.
So I've got a couple of questions from the audience right now, and I like this one here. This one comes from War Basher, which is, if you're developing are you developing some ways to predict and time supernovae? What about Betelgeuse? And I think that's a question that's on all of our mind. When will Betelgeuse explode already?
Explode! I really want it.
Yeah.
It's going to be great. I'm really waiting for this. I hope I'm alive for another 20,000 years. But these are the sorts of things like Betelgeuse, and we did this with the supernova 1987A. So this occurred in the Large Magellanic Cloud. By being so close with some of these, we can measure them beyond just our normal telescope colors, our normal optical colors. We can see particles, neutrinos, and now in the era of gravitational waves, if Betelgeuse blows up, we'll detect the wave of gravity going through space, and being able to probe the light time versus the gravity time and really actually measure independently these things. So I hope that it blows up any day now, because it would be cool, and it would allow us to just see things that we never did, and that's what 87A in the Magellanic Cloud did. So go Betelgeuse!
I mean, we apologize for the terrible disaster that will befall anyone who's near.
We'll have a moment of silence for the Betelgeuse system. Yeah.
But we will gaze on it in wonder in the middle of the day, which is great. We've earned it.
Exactly. Yeah. We're due.
We usually don't see things that change in the sky, like stars changing with the naked eye, but we will be able to do that with a Betelgeuse. So that's something mind-blowing.
Now, Brad, before we started the show, you actually mentioned to me some kind of exciting uses for the Kepler space telescope that I wasn't aware of.
I mean, a lot of people are aware that two of the wheels that helped Kepler point broke, and so there was this new mission called K2, and so it kind of rotates now between looking at planets and then galaxies. And we've actually been using SkyMapper to work with Kepler and discover supernova. And so with Kepler, you can actually see within minutes the explosion. And so the end of K2, so it's about to run out. Dedicated to actually finding exploding stars. So SkyMapper will be looking at the same exact patch of sky Kepler is, and we're going to see in detail, the subtle things that happen with SkyMapper and supernova that we can't see normally because we only observe it once a day, but we'll be seeing it every 30 minutes. And so citizen scientists can look in the SkyMapper database and find exploding stars that are helping Kepler. And so it's a really cool.
Great. How are the wheels doing? You brought this up earlier.
Yeah, the wheels are actually doing quite good. So what happened was when they landed on a surface that was the kind of surface they had designed the wheels for, mostly sandy surface with some loose rocks strewn around, and that kind of surface wheels have no problem with. But about 350 sols into the mission, they started putting a lot of miles on the wheels, and they were deliberately driving on the tops of ridges so they could have real long distant views, which is what they need to plan fast driving. And it turns out that the resistant tops of the ridges had very hard rock that was very pointy, wind eroded into ventifacts. And the most important thing was that those pointy rocks were solid parts of rocks. They weren't just loose pieces of rock that could roll around under the wheels. Engineers described them like shark's teeth embedded in concrete. And so when the rover started driving over those, just having a wheel drive over one of these won't cause a problem. The wheels are strong enough not to poke into it. But because of the dynamics of the wheel system, there would be like a wheel on the end of an arm, and it would get pushed onto this, and then it would get shoved in as the other wheels were rolling it forward. And so that is what started damaging the wheels and poking the big puncture holes in them. And so they realized this pretty quickly, and realized that the way to deal with it was prevention. And so they had to stop driving on the tops of those ridges. They had to get into safer territory. And it wound up being kind of a cool story, about how the science team used orbital images to map, not just for geology, but also looking for wheel shredding rocks. And there's actually now a scientist, a tactical role on the mission called the surface properties scientist, whose job it is to sit at the elbow of one of the engineers and say, that terrain over there is not safe, avoid it, you should drive around over there, and then you can get to, and that terrain is not wheel shredding. And so by doing that, they've actually dramatically reduced the rate of damage on the wheels, and I think there's little doubt that the wheels are going to survive as long as the rover does.
And then future missions will be able to take advantage of this little piece of knowledge for their wayfinding into the future.
Yeah, Mars 2020 has different wheels.
It has those like chainmail looking ones, right?
No, it doesn't. It has, they actually look like a cross between Curiosities and Opportunities. They're a little narrower and they have treads set more closely together.
Right.
And so they'll be stronger and stiffer. That's the other thing, is that the Curiosities wheels were deliberately made very thin and flexible because it's the landing gear for the rover. And so they were made to deform a lot and then return to their shape. But it turns out that deformability, when you bend a paperclip back and forth and back and forth and back and forth, it finally snaps. It leads to just tears, just rips that are caused by fatigue. And so the new wheels on 2020 will be thicker so that they won't bend back and forth so much, and there will be less fatigue.
Right. All these lessons learned.
Yep.
Arjon's got a great question in the chat, which is, well, his first question is how many different experiments can Curiosity do, but have there been any experiments done that it wasn't originally designed for? And I think that's one of my favorite parts about some of these science missions is when they figure out how to make a spacecraft find something that it wasn't originally intended to do. So how's Curiosity been in that department?
Yeah, there's been a couple of cool ones. One is I think more fun, and that's the Chemcam instrument. So the Chemcam is the laser beam on the rover's head. It fires a laser, it turns a little bit of rock into plasma, and it has a spectrometer that looks at the colors in the plasma to identify the elements that are in it. And because the laser only vaporizes a really tiny point, they attached a camera to it that can take a little context image that shows you the rock area around where they zapped. And there's another interesting piece of trivia. The camera instrument is a flight spare of one of the cameras from the Philae lander on the Rosetta mission. So that's kind of cool. But backing up, so Chemcam has this camera that is mostly used for taking context pictures. But because its focus laser broke, they developed a new way to focus it that actually allowed them for the first time to focus it at very long distances. And so now they use it like a spyglass. They can take